well, next we're gonna look at other popular configurations of operational amplifiers. Popular configurations of op-amps. Other popular configurations of operational amplifiers, other than the feedback configurations. In terms of feedback configurations, we studied non-inverting amplifier, inverting amplifier, as well as voltage follower. Now, the other popular configurations of operational amplifier include what we call a summing amplifier. What is a summing amplifier? It's also referred to as a summer. So it's an analog summer because it performs the sum, as you can already predict. So a summing amplifier is basically an amplifier that of which the output is somehow the sum of the input voltages. But now, for it to be the pure or absolute sum of the input voltages, there are some conditions that will come with, because remember, it's all current oriented, and the fact that we've got a couple of resistances on the input for each input voltage, that obviously result in having a portion of the input signal only being amplified. But let's just look at the configuration itself. So in general, a summing amplifier looks like this. It's normally an inverting amplifier mode, in which we've got a single feedback resistor RF, but we've got, instead of having a single input voltage and input resistance, therefore we get multiple input resistances. We're gonna call them R1, R2, R3, etc., all the way to Rn, and therefore we have multiple voltages applied to this input. This will be V1, V2, V3, all the way to Vn. So that's how a summing amplifier in general looks like. So now, if we have to do the analysis on this, is that VID is still 0. That makes the voltage at that point to be equal to the voltage at that point. The voltage at this point being 0, that will behave once more like a virtual ground. So it's going to have 0 volt there. So as we have 0 volt there, we're going to have current flowing from the high voltage potential towards the low voltage potential on the input side. And since we've got multiple networks of the circuit, we're going to have multiple currents as well. I1, I2, I3, and IN. On the output side, we go from V out to ground, and as we go from V out to ground, we've got current, output current, sometimes referred to as feedback current, flowing in the opposite direction to the directions of the different input currents. Now, if we apply Kirchhoff's current law at the inverting input of the amplifier, which says that the sum of all current going into the node is equal to the sum of current going out of the node, then we have I1 plus I2 plus I3 plus IN, which are the current going into the amplifier, plus IF. And since there's no current going out of the going into the node, and since there's no current going out of the node, that will make it 0, right? So that will lead to I1 plus I2 plus I3 plus IN being equal to IF. All right, or I out. IF is also I out. Okay, sorry, minus IF or minus I out. It's the negative side. Okay, and that leads to if you have to assess each of these currents, remember I1 is the current from V1 to ground to this point, and that point being a virtual ground. I1 is nothing but V1 divided by R1. I2 similarly is V2 over R2. I3 similarly is V3 over R3, etc. In will be Vn over Rn. The same way, I out, which is equal to If, will be nothing but V out divided by Rf. So if we go back to the Kirchhoff's current law equation we had, then we're gonna basically have V1 over R1 plus V2 over R2 plus V3 over R3 plus Vn over Rn is equal to minus V out over Rf. That leads to V out being equal to minus Rf times V1 over R1 plus V2 over R2 plus V3 over R3 plus Vn over Rn. As we can see, at the end of the day, the output voltage, although inverted and multiplied by some parameter, is still equal to the sum of portions of the input voltages. I say portions because each time the input voltage is multiplied by Rf over R1. Is that okay? And then multiplied by Rf again over R2 for V2, and V3 is multiplied by Rf over R3, etc. And Vn is therefore multiplied by Rf over Rn. So under the condition that Rf is the same as R1 and R2 and R3 and Rn, in other terms, if all resistors used in the summing amplifier are equal, we will end up with V out being simply minus V1 plus V2 plus V3 plus Vn, because Rf will cancel with each of the resistors, right? And it's for that reason that we call this amplifier summing amplifier. Okay. All right. That concludes the summing amplifier. It has got plenty of applications. Let's say you want to do a typical application of a summing amplifier is basically a mixer. With a mixer circuit, you've surely heard about a mixer circuit. Maybe in the sound engineering application, you normally mix two signals together, right? So one way you'd think about it is V1 will be the one signal, V2 will be the other one, and they will come out, the output of the summing amplifier as a single signal V out. That is a combination of the two added but of opposite phase, right? That's the minus there, shows that it's opposite phase. But at the end of the day, a mixer will be a typical application of a summing amplifier. Since we are studying popular amplifier configuration, we're going to look at another popular amplifier configuration that is called the difference amplifier. Difference amplifier. The textbook says differential amplifier. That's another one way to look at it. But another good way to call this is to say difference amplifier, just to make a bit of differentiation between a differential amplifier, the way we learned it, and an actual operational amplifier that is used as a difference amplifier, meaning used and configured to come up to amplify the difference of two signals, right? So the typical configuration will look like as follows. We've got the inverting pin, which is connected to a feedback resistor all the way to ground, and from there we've got a first input resistance R1 to V1, and on the non-inverting side we also have R3 to ground and R2 leading to the second voltage V2, and then we've got V out. If we analyze this, VID, the guiding principle is that VID must always be equal to 0, which means that voltage there must be equal to that voltage here. So let's call that point A.